All right, so this is the second video for Unit 13. This is a continuation for solids of revolutions and volume equivalency. So again, we will be comparing shell and disk and washer and talking about which one would be more convenient for you from a timing standpoint. So for number 4, we have y is equal to natural log of x, y equals 0, x equals e, and then we have that y equals 0 again. Just ignore that because it's a repeat. And this area is being revolved about y equals 0. So in reality, you will have to make your own sketch usually, most of the time. So understanding which function is what will be very helpful. So this upper curve is going to be y equals natural log of x. At y equals 0, we are crossing the y-axis at 0. So the tan is y equals 0. And I'll go ahead and underline. And then x equals e, that's going to be a vertical line passing through e along the x-axis. So our shaded region is going to be in the yellow, bounded by these three functions. And the first recommended method is the shell method. So hopefully you watched the previous video so you recall why it is 2 times pi times r times h. What I failed to mention in the previous was what the dy represents. That represents the thickness of each shell, all right? So they are very, very small, but that is just there to represent the thickness of each shell, which is why we are integrating with respect to y, okay? For our r, that is going to be the distance between the bar and the axis of revolution. So in this case, the axis of revolution is at y equals 0. And then the bar is going to be vertical. So it'll be top minus bottom. So wherever the bar is, it's going to be a y value. The upper bound is the y value. But then if you do top minus bottom, the lower bound will always be 0. So we have a sliding scale along these y values within the shaded region. So that's why the r is just equal to y. The h will be right minus left. So the right side of this is x equals e, so we can just use e. But the left side is y equals natural log of x, but we are integrating with respect to y, so we need to rewrite this in terms of y. If I exponentiate both sides, we get e to the y is equal to e to the natural log of x. E and natural log are inverses. So we get e to the y is equal to x. So that's why we have e minus e to the y. Once we have our r and our h, we can go ahead and plug it into the integrand. So we have y times e minus e to the power of y. Bounds of integration are going to be vertical since we are integrating with respect to y. We already have this bound, this lower bound, which is y equals 0, so that will be our lower bound. Our upper bound is where these two intersect, okay? And if I set these two not equal to one another, but I know x is equal to e, and then our function is y equals natural log of x. So we can just substitute e in for x. Natural log of e is going to be 1, so that will be our upper bound. Once the setup is there, we have multiplication within our integrand. So that means we will be using integration by parts. And again, in the previous video, we talked about how to determine how we will do integration by parts. We use liate. Again, L is natural log, I is inverse trig, A is algebraic, T is trig, and then E is exponential. In this one, the first out of these letters is algebraic because the E minus E to the Y is exponential. So whenever you occur or have algebraic occur first, you can use your tabular method, which is quick, all right? So just be careful with the setup though. We always start with a plus and we alternate plus minus depending on how many times you can differentiate your algebraic expression. So the algebraic expression is y. Differentiate y, you get 1. Differentiate 1, you get 0. Okay, so we only need 3 rows for this one since that's how many times it took to differentiate y before we got to 0. Now in the other column, we will start with our exponential expression, which is e minus e to the y. Because we differentiate this first column with respect to y, you will integrate with respect to y the second column. When we integrate e with respect to y, it's a constant, so we get e times y. And then when you integrate e to the y, it's just e to the y. And then when we integrate again, so that we can fill up the last row, we integrate y with respect to y, we get 1/2 y squared, but we have that constant e minus integrating e to the y is just e to the y. So now when we want to write our integration by parts expression, remember you use the first two and then you drop down for the last part, and that is your first term. So we have positive y times e times y minus e to the y. Next, we do the same thing, but for the second row. So we have minus 1 times e to the y, e over 2y squared minus e to the y, but you distribute that negative, so we get negative for the first term, positive for the second, and this is being evaluated from 0 to 1, okay? From there, it's first fundamental theorem of calculus, and we end up with pi times e minus 2, okay? Now we want to try the disk method, all right? Well, we can already assume that it looks like shell method the setup is a little rigorous, but the algebraic manipulation was quite simplistic because we didn't have to do so many things within the actual formula itself. But let's see if we get lucky with the disk method. So for disk method, remember that your bar is going to be perpendicular to the axis of revolution, right? Unlike shell method where your bar is parallel to it, okay? So for this one, we only need to find r, which is going to be top minus bottom. Now the short side of the bar is horizontal, so we are integrating with respect to x. So if we look at the top of this function, since we are integrating with respect to x, we can just stick with using the natural log of x. Okay, so we'll have natural log of x minus the bottom, which is just 0. So within our formula, we have pi. We'll figure out the bounds of integration in a second. R squared is going to be natural log of x squared dx. Bounds of integration, if we look, we can see that this is crossing through the x-axis at 1, but if you really want to be sure, you can plug in 0 for y. Okay, so we have 0 is equal to natural log of x. And I'm doing this because the output here, it's 0. Okay, exponentiate both sides, we get e to the 0, e to the natural log of x. E to the 0 is 1, and then this becomes x. So the lower bound is 1. Upper bound is going to be whatever this value is. This is x is equal to e, so the upper bound will be e. Again, I know e is a constant, there's a decimal value for it, but use the exact, stick with the variable e. All right, from here we have a special case. All right, so whenever you have a log or inverse trig, whenever they are an isolated integrand, you will use integration by parts. These are the only two cases on this exam where you use integration by parts when it is an isolated term, okay? So we will use integration by parts for this one. So we need our u and we need our dv to start off. Our u is going to be the natural log of x squared, which means our du, we will use the chain rule for this. So it'll be 2 times natural log of x. The derivative of the inner function, which is natural log of x, will be 1 over x. And then do not forget your dx. dv, this is where some students get confused. They're like, I already used everything. No, you didn't. All right, we still have dx here. So dv is equal to dx. So whenever you are using integration by parts for isolated expressions like natural log or inverse trig, your dv will be the dx. So when we integrate dv and dx, we just get v is equal to x. And a lot of you brought up a good point. What about the plus c? I mean, you can write it. It's a means to an end. We are technically working within the bounds of a definite integral, so that c will go away, but you don't need it. You won't get docked for it, I should say. All right, so expanding this, remember your ultraviolet voodoo. So the volume is equal to, we have pi on the outside, and the ultraviolet, that will be u times v. So we have u times v. I'm going to put the x in front just so that I can clearly see the separation. So we have x times natural log of x squared, and then minus the integration of v, which is x, times du. So du is going to be all of this. So times 2 natural log of x times 1 over x times dx, close the bracket. All right, always work on simplifying before trying to move to the next step. It does add a column to your vertical work, but it will help you prevent algebraic mistakes that might prevent you from getting the correct answer. Okay? And you've already done the hard part. Like now we're just doing algebraic manipulation. We might have to integrate one more time and then use the first fundamental theorem of calculus. But there are a lot of moving parts, so just double check yourself. I always say don't try to skip steps, and then don't try to play like, you don't have to show off to your AP reader, okay? Showing off is when you are communicating that you understand what's happening. It's not about skipping steps and making yourself look smart. I mean, you're in this course, you're already smart. Show all the steps you need to so that you don't make any mistakes. Okay. So from here, we have x natural log of x squared. Simplifying, I see that the x's cancel out. And then I can go ahead and bring the 2 in front of the integrand. So we have 2 natural log of x dx. And I again have a natural log expression that's isolated. So we will use integration by parts again. I'm going to use a subscript 2 since I already used u and v. So I'm going to do u sub 2 is equal to natural log of x, which means my du is just dx. And then my dv is going to be dx, and then my v is just x. The subscript, I don't believe that you will get docked for that. I'm going to be honest, because again, it's a means to an end. We already used u, but I'm just being super nitpicky. I will not dock you for that on your assessments. You're already doing enough as it is. Okay. All right, so moving on, let's see, we have the volume. Let's move it down a little bit. So now this is where notation is important. I have my x times natural log of x squared out front, minus I have my 2. My integration by parts is starting here. Okay, so we're coming back to ultraviolet voodoo. My u is going to be natural log of x, and then my v is just x. So we'll have x times natural log of x minus the integration. My v is x, my du, my du, oh no. First off, my du is not just dx, it should be the derivative of natural log of x, which is 1 over x, and then my dx. And then 1 over x times dx, close the first, and then we have our second bracket. All right, so I see that the 2 x's cancel out here, so we're just integrating dx. So volume is equal to pi times x natural log of x squared minus 2 times x times natural log of x minus, when we integrate 1, we just get x. Close it off, we're integrating from, 1 to e. So I purposefully kept my bounds off until I was done integrating everything, okay? That's okay, that's acceptable notation. I didn't even include them here because I knew that it would also affect the rest of this, so I just kept it all blank until I got to the very end when I was done integrating every single part. I'm not gonna lie, I don't know the specifics of that as far as scoring on the AP exam, but I will look it up so that I can let you know before the AP exam. Okay, so before we apply the first fundamental theorem of calculus, I'm going to go ahead and divide and see if I can combine any like terms. So I have x natural log of x squared. Distribute the 2, I get minus 2x natural log of x, and then I have plus 2x. Keep writing 0. All right, it looks like there's nothing to combine, so we'll go ahead and apply the upper bound and the lower bound. All right, for the upper bound, we have e times natural log of e squared minus 2e natural log of e plus 2e minus the lower bound, which would be 1 times natural log of 1 squared minus 2 times 1 times natural log of 1 plus 2 times 1, and then close the big bracket. Hopefully this simplifies to something a little bit simpler. Natural log of e, that is going to be 1. So we have 1 squared times e, which is just e. And then again, we see another natural log of e, that is just 1. So we have minus 2e, and then plus 2e. And then natural log of 1, that's going to be 0. We have another natural log of 1, that's 0. And then we have plus 2. So we have minus 0, plus 0, and then this negative sign will negate that, so we have minus 2. All right, so the minus 2e and the positive 2e cancel out. We don't need to worry about the zeros. So we have pi times e minus 2, which I think that was what we got with the Yes, with the shell method. Okay. So obviously the shell method is more efficient than using the disk method, which is why I'm suggesting that you keep shell method in your arsenal because, again, you can save a significant amount of time with that method. Now, disk method, it was just integration by parts, but it was twice, a lot of algebraic manipulation, but the tabular method, we got away from a lot of that, okay? So now we are switching gears to volumes with cross sections, and we will need the calculator for this. How do I do this? Okay, there's a recent update, and it took me a while to figure out how to do it. Okay, so now move this over, and the adds came back. Okay, let me get rid of the adds real quick, and then we'll continue on with cross sections. Nice, okay. Now that I understand how to do it. All right, so volumes with cross sections, just a quick reminder that we do not revolve around an axis. No revolution about an axis. So we will start with an area, all right, between two curves. And what's going to happen is if you have this area, that's the base of our solid, all right? It's not moving, it's not shifting, it's not changing. But then after that, the shape is going to come out three-dimensionally. So if you're looking down at your paper right now, or if you're looking down at your paper, it would come up at your face along the z-axis, which would be perpendicular to the surface that you were looking at. If you're looking at your computer screen or another screen or the whiteboard, it would be coming at you directly, so it would be coming out perpendicular to the surface that it's starting on, okay? All right, so this says the base of a solid is the region bounded by y equals e to the power of 1/3 x, and then we need to change that. This should all be minus 1. So y is equal to e to the power of 1/3 x, all minus 1, and y equals 4 square root of x. So this is a calculator app, so we can go ahead and type it in. Y1 will be second e. We will have 1/3 x, all minus 1. Y sub 2 will be 4 square root of x. So again, I'm going to go to zoom 0, which is zoom fit. See what I get. Okay, so it kind of worked out. The whole thing is in the screen, so I'm going to go ahead and keep it like this. And then what we want to try and do is we want to set up an integration to get the area of the bounded region. So I'm going to do a quick sketch. The upper bound will be the red, which is going to be, that's the square root function. The lower bound is going to be the exponential, which is the blue, okay? And we are looking at the region bounded by these two curves, which will be the base for our three-dimensional solid. All right, so just like we talked about previously, we need to find the bounds for this base and its cross sections, and our functions are already in terms of x, so you might as well integrate with respect to x, all right? And that's because the small part of the bar is here, which is horizontal, okay? So both of our functions are in terms of x, and also consistently, the upper bound is the same function and the lower bound is the same function. It's consistent across the entire bounds of integration, okay? So we'll set this up. So to find the area, we will do top minus bottom. The top function is 4 square root of x. The bottom function is e to the power of 1/3 x minus 1. And integrating with respect to dx. Bounds of integration, it looks like 0. You can go ahead and test it. So second trace, number 5. We're already close. We can hit enter, enter, enter. All right, and it says 0, 0. Okay, so they are intersecting at x equals 0. So because we're integrating with respect to x, your bounds should also be in terms of x. Second trace, number 5. Let's get closer to the second intersection. And we get 7.43. Okay, so x is equal to 7.430. And it says find the area of the base. Okay, so if we want to find the area, that's the setup. So from here, we can go ahead and type it into the calculator. All right, so alpha window, go to number 4. We're going from 0. Uh-oh, I don't want to use the approximate. So I just found that in my graph, right? So if I hit second answer, it should have saved it. Nope. Let me try that again. Or I might be able to store it. So if I go back to my graph, second trace, number 5, hit enter, 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 I get 7.43052, da 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 da. So if I go back, I hit second answer, and there's my value, okay? Now I'll do my integration. Number 4, we're going from 0, and I want to use that again. So I'm going to go up. Oh, maybe it won't let me. Second answer. Will it do it? It's because I'm hitting enter when I shouldn't be. Okay, so I'm going to copy this. Watch it not work. So alpha trace, we saw which one was which. So the exponential function was the lower bound, so we will do y2 minus y1. So second trace, y2 minus second trace, alpha trace, minus y1, and we are integrating with respect to x, and we get 28.732. All right, so the reason why I use the answer function in here is because I don't want to use the approximation. I want the exact from the calculator, okay? So after you trace in the graph, whatever you trace, it'll save the x value. You can just go back to your home and hit like second answer, or just use second answer in your integration. Okay, part B says find the volume to the nearest thousandth of a solid where the cross sections taken perpendicular to the x-axis that are equilateral triangles. Okay. So we have this same region bounded. Our upper was the square root. The lower is the exponential. Okay, and we have this region here. All right, so this said its cross sections are perpendicular to the x-axis, so that means we are integrating with respect to x, okay? Perpendicular. So the equilateral triangles, the base of all of these triangles will be between the upper curve and the lower curve. And since they are equilateral, that means all 3 sides will have the same length. And we have an infinite number of these triangles that are coming at your face. So the point, the tip of these triangles are coming at your face. And if you think about it, the equilateral triangle in the number in the middle has the longest base. Therefore, it will be the highest point of this shape. And then if you look at the triangles on the edge, they have a short base, which means the height as it's coming out of your paper towards your face will be lower. So it kind of looks like a mound. And then as we get closer to the center, the mound is getting higher, okay? Okay, so for these equilateral triangles, the base is going to be top minus bottom, okay? Which we already did up here. We already did top minus bottom here. But something else that's going to change is we now want the volume, okay? So we're going to have to multiply this in a way where the volume is found using these equilateral triangles. Well, back when we did cross sections, I showed a method for why we use this, and it's based on the area of a triangle. So for equilateral triangles, you have to remember √3/4b squared. So if you want to go back and look at that, you can. It's in units, which unit was it? It's in the volumes unit. I think it was unit 7, all right? So if you go back to unit 7, look at your note packet and then go back through those pages. In the cross sections, you'll see the explanation for that, okay? All right, so now when we find the volume using these equilateral triangles, I know that my B from here, it's going to be top minus bottom. That's going to be 4 root squared or square root of x. And then when I do the minus, I'm going to distribute it to both terms. So I get minus e to the 1/3 x and then plus 1. So that is our base for top minus bottom. All right, so the volume, we have our root 3 over 4, and that's for equilateral triangles. And we're going from 0 to 7.430. And then we have our base, which is 4 square root of x minus e to the 1/3 x plus 1. And this will all be squared, and we're integrating with respect to x. So I'm going to go back home. If I want to find the volume of this, I already wrote it, and I already have this set up here, so I'm going to copy it. I'm going to go to the front and then include that constant. So second insert, second square root. Actually, let's do alpha length to get that fraction bar. Square root of 3 divided by 4. All right, and then something else we need to add is the squared. So second insert, get a parentheses, and then another parentheses so that we can get the squared in there. Enter, and we get this. This is a pretty large number. A very large number. Double checking. Let me try it again with the 7 point. Where'd it go? That should be x. Oh, I bet it changed the answer because it was the previous answer. No. Okay, delete. So what I'm going to do is, I wish I could just copy it. Enter. Oh, there we go. Okay, so I went up and highlighted it and I put back the 7.43. There we go. So when I have the answer in there, it literally took that 28.732 and made it my upper bound, which is incorrect. So that means this will have a value of 54.373 units. All right, and now the next part says we are a solid where the cross sections taken perpendicular to the y-axis are semicircles. Jeez. Okay, so we have the same bound, region bounded. It's going to be in here. And now the cross sections are semicircles. So that means the diameters of these semicircles are in between these two curves. So again, we have a three-dimensional shape coming at you. It's no longer a point, it's a smooth curve. But as we get closer to the center of this, the curves get closer to your face or higher because they have a larger diameter. So if we think about this, we're starting at 0. That first semicircle, that coordinate point will be 0, 0. And then we have an infinite number of semicircles. They get bigger, and then they start to get smaller as we get to the back. And then that very last point is going to be the y value, the x value is 7.430. I'm not sure what the y value is. But I'm going to have to find it because we are integrating. Oh, it's perpendicular to the y-axis. So all of my circles are the wrong way. Sorry about that. I did it if it was perpendicular to the x-axis, which means we have to do right minus left. My semicircle should be going this way. That way it's actually perpendicular to the y-axis. So again, we still have that 0, 0. And then as we, oh, I did it the right way with the sketch down here, but it's fine. They get larger, and then as we get closer to the back, they get a little bit smaller. And we have this point here where it's 7.430, and I'm not sure what the y value is. All right, so the area for a semicircle, again, if you want to get all of that, you can go back to the unit and look for the explanation. It's on the same page as the equilateral triangle. The formula for this is pi over 8b squared. Pi over 8b squared. But also, we need to rewrite this so that both expressions are in terms of y because they are perpendicular to the y-axis. So let's start with the first one. The first one is y is equal to e to the 1/3 x and then minus 1. All right, so we'll do plus 1 is equal to e to the 1/3 x. And then we need to take the natural log of both sides because the variable is in the power. So we'll take the natural log of y plus 1 is equal to 1/3 x. Multiply both sides by 3, we get 3 natural log of y plus 1, which is equal to x. So there is our first. This is actually the upper bound. All right, so if I set up my integration, we'll set it up down here. That will be my first part. So 3 natural log absolute value of x plus 1. I'm sorry, y plus 1. All right, now we need to do the second one, which is this 4 times the square root of x. Divide both sides by 4. And now square both sides. Can't get a break. And now square both sides. So we have y divided by 4 squared, which is equal to x. So we get y squared over 16, which is equal to x. Okay, so now this is the lower bound, so we will subtract that. So minus y squared over 16, and then all of this is squared dy. Now the bounds of integration, we are crossing at the origin, but now we need to find the y value, which is fine because we found it in here already. Second trace number 5. Now instead of looking, oh, weird, well, let's try it again. Enter. Okay, so the y value is going to be 10.903. And then that's where we'll stop for this one. Like, to get the actual volume, you can type it in using x. You don't have to try and rewrite everything back. So you could type this in using the x in your calculator and you will get the volume. All right, number 6 is Euler's method. So we're going away from cross sections and revolutions, 3-dimensional shapes. So given the differential equation dy dx is equal to x plus 3y, use Euler's method with delta x equals 0.2 to estimate y when x is equal to 3 for the solution curve satisfying the y of 2.6 equals 5. Show all work. Okay, so for this one, you want to notate some of the things that you're giving. We know where we are starting, x naught and y naught, that is equal to 2.6 and 5, okay? So that's where we are starting, and we are using Euler's method to approximate when x is equal to 3, and we have delta x is equal to 0.2. So what you want to think about for this is basically the equation for a line, because that's what we are using. We are using multiple tangent lines in order to get the approximation here, okay? So we have y sub 1 is equal to y naught, Chloe, plus dy dx times delta x. So we have where we are starting, then we have our dy dx, and then the change in x, and this is going to get our approximation for y sub 1. All right, so y naught, we are starting at 5. So we'll have 5 plus, and then from here, dy dx, we want the value for that coordinate. So it'll be x plus 3y, okay? So if I plug in x for that one, the first x is 2.6, and then plus 3 times y, we have 3 times 5, which is the y, and then times delta x, the change in x is 0.2. All right, so we do have a calculator. Again, be time efficient. So we'll have 2.6 plus 3.5, and then times 0.2, and then plus 5. So we get 6.22. I multiplied. Hold on, let me try that one more time. 2.6 plus 3 times 5. Okay, so plus 15. I saw that as a decimal. My bad. And then times 0.2, and then plus 5. So we get 8.52. I would get in the habit of just writing the full coordinate point. So that way we have 2.8, 8.52. And I know it's 2.8 because we started at 2.6. Change in x is 0.2, so 2.8 plus 0.2 will be 2.8. All right, we're not quite to 3 yet, so we're going to do this again. So now y sub 2 is equal to y sub 1 plus dy dx times delta x. So y sub 1 is going to be here. It's what we found in the previous section. So that'll be 8.52 plus dy dx. We now use this coordinate here in order to get dy dx. So x is going to be 2.8 plus 3 times y, which is 8.52, times delta x, which is 0.2. So dy dx will be different for every single tangent line because we want to plug in that coordinate point. That's why Euler's method is more accurate than just tangent line approximation, because as we get closer to the point that we are approximating for, the slope is getting steeper or less steep depending on the rate of change for the curve. All right, typing this in the calculator, we get 2 points. Let's start with the multiplication. So I have 3 times 8.52, then I have plus 2.8, and then times 0.2 plus 8.52. So we get 14.192. And this is going to be 2.8 plus the delta x, which is 0.2. We get 3, and we have 14.192. So it wants to estimate when x is equal to 3, therefore f of 3, or I guess I'll say y of 3. Everything's dying. Y of 3 is about 14.192. All right, so solving differentials, we have time for a little bit more. Solving differentials, the rate of change of p with respect to t is inversely proportional to the cube root of p. Write the differential equation and proceed to solve for the particular solution given p of 0 is equal to 8 and p of 1 is equal to 27. So the first thing that you want, this is separation of variables. Separation of variables. And with these, you have to create the equation. So if you have direct proportionality, that would look like k times p raised to the power of 1/3. Okay. This says we are inversely proportional, which means that they will not be multiplied, they will be divided. Okay. So the rate of change of p, so rate of change of p with respect to t, that's going to be dp over dt, is inversely proportional to the cubed root of p. So that means dp dt is inversely proportional, which means we'll have this in the denominator, and then now we will have our constant of proportionality in the top. So write the differential equation and proceed to solve for the particular solution. So that's our differential equation. I believe it's either 1 or 2 points if it's a free response, okay? So now from here, the separation of variables, this is where it starts. We're going to cross multiply. So I have p to the 1/3 dp is equal to k dt. Now k is a constant, right? So we're fine there. Once you have your variables separated, integrate both sides. The integration of p to the 1/3 is going to be p to the power of 4/3. Coefficient will be 3/4. Integrating k with respect to t, we get kt, and then plus our constant of integration. Now again, we only include the c on the second one because it's basically, it accumulates all the plus c's. There's 2 plus c's, but we just make them one constant, okay? So you don't have to worry about the plus c on the left side. Now from here, we are solving for a particular solution. We already have our general form, but we want the particular, which means we can use this and or we can use that, okay? So from here, let's plug in 0 and 8. If I plug in, we have 0 for t. Let's go ahead and start here. So I have p of 0 is equal to 8. So that means t equals 0, and then p is equal to 8. So plug that into our general form. We have 3/4 of 8 raised to the 4/3 is equal to k times 0 plus c. All right, so when we manipulate this algebraically and reduce it, we end up with, well, we have a calculator. Let's see, we have 8 to the 4/3, which is going to be 16 times 3 divided by 4. We have 12, and I'm doing this for time because I'm running out of it. So 12 is equal to C. So our constant is going to be C. Now this is why we have the second point, is that we also need to solve for K. So now we'll plug everything back in to our general form, including our C, to solve for K. So we have, this is P of 1 is equal to 27. Therefore, T is equal to 1. P is equal to 27. So we have 3/4. 27 raised to the 4/3 is equal to K times 1 plus the 12. Now for this one, we have 27 raised to the 4/3, and then times 3 divided by 4. We end up with 60.75. So we get K plus 12, and then when we subtract 12 from that, we end up with, didn't want to add 12, I wanted to subtract, minus 12. We get 48.75 is equal to K. So our particular solution will be 3/4 P raised to the 4/3. Our K is 48.75 T plus 12. So that is our particular solution. All right, and our last problem is number 8. So it says find, I do not think, we do not need the calculator for this one. Okay, so it says find the particular solution to the differential equation dy dx is equal to 3y plus 2 given y of 2 is equal to 4/3. Okay, so we have our differential equation, and we are using separation of variables again, okay? Now remember, we talked about this before, you rarely should be adding or subtracting. For separation of variables, you should be working on multiplying and dividing. So technically this is all over 1, so we need to separate the dy and the dx so that we can integrate each individually. And so let's go ahead and cross multiply. Okay, so basically what's going to happen is the 3y plus 2 will go to the denominator, dividing both sides by 3y plus 2, and then I'm multiplying both sides by dx. So this way, all of our variables of y are on the left, and then all the variables for x are on the right. Once your variables are separated, integrate. So when we integrate 3y plus 2, that is going to be u substitution. So let's say, actually, let me rewrite this. So we'll have 1 over 3y plus 2 dy is equal to the integration of dx. So u is equal to 3y plus 2. du is equal to 3 dy. And we do not have a coefficient 3 in there, so we will divide du by 3, so we just have the dy. If I had a 3 here, we'd be good, but we don't, okay? So now from here, we can rewrite our integration. We have the 1/3 out front. And then when we integrate 1/3, we can have 1 over u du, because du over 3 is equal to dy. I have my 1/3, I have my du, so it takes care of the dy. And then u is equal to 3y plus 2, so we're good. When I integrate x with respect to x, it's just x plus c. Integrating u, I have 1/3 natural log of the absolute value of u. I already have my c, and then u is equal to 3y plus 2. All right, so we have our general form, but now we're given an initial condition. So we'll do what we did up top. We will plug this in. So we have x is equal to 2, and then y is equal to 4/3, because we want to solve for c for this particular solution. So we have 1/3 natural log of 3 times y, which is 4/3, plus 2 is equal to 2 plus c. All right, so we have 1/3 natural log. The 3's cancel out, so we have 4 plus 2, which is 6, is equal to 2 plus c. So we get c is equal to 1/3 natural log of 6 minus 2. And that's okay. So if we come back to our general solution, we have 1/3 natural log, the absolute value of 3y plus 2 is equal to x, which is 1/3 natural log, x plus, and then we have our c, which is 1/3 natural log of 6 minus 2. And there's our particular solution. There's no need to isolate anything. Once you have all the variables that you need and it's written in terms of x and y, you are done. Move on to the next problem. All right, if you made it this far, nice job. I know that was rough, but I hope this helps.